Well, now let's turn our attention to the expected return on a portfolio of stocks, assets, securities, whatever. The expected return on a portfolio is the weighted average of the expected returns on the assets in the portfolio, where the weights are the proportions of portfolio value. Now, we saw an example like this early on, so we're repeating it here. And here's the formulation. These weights, remember, these weights are the proportions of the portfolio value that's invested in each of these N securities. Now, if we wanted the expected value instead of returns, we could just put in a dollar value or a euro value or whatever currency we're using. And the weights are still the same. The weights are, if 20% of the portfolio is invested in stock A, then that's the weight we use on the expected return on stock A in calculating the expected portfolio return. Now, this LOS here wants us to calculate the variance of portfolio returns. So we've got two different assets now. We've got asset A and we've got asset B. And we're putting them in a portfolio in some weights, right? 60% in A, 40% in B. We know that the weight in A, and that's our WA here, and the weight in B add up to 1. And that's because we've only got two stocks in our portfolio. Now, this formula, look at first the intuition of it, the things that matter. We're looking for the variance of the return on the portfolio. Well, what's that going to depend on? Well, it's certainly going to depend on the variance of the two securities we're putting in the portfolio. And it's certainly going to depend on how much A we put in and how much B we put in. But this last term here, 2 weight in A times the weight in B times the covariance, that's the adjustment for how they move relative to each other. Now, if they just move in lockstep, okay, that is a strong covariance, then that variance of the portfolio is going to be greater than if this covariance term were smaller or negative. If it's negative, then this whole term is negative, and we're really subtracting that, driving the portfolio variance down. Now, you may have occasion to use it in this form, but we'll also see this equation in another form. And the other form is we substitute in for the covariance. Well, remember, we had correlation equals the covariance over sigma A, sigma B. So this is the covariance AB and the correlation AB. Well, if we just multiply both sides of this equation by sigma A, sigma B, this cancels out. We get sigma A, sigma B over here. And so that's why we can substitute that in for the covariance right here, this term, and then we have it like this. And now when we look at it, if that covariance is positive between 0 and 1, then that term is positive and increases our calculation of the variance. If that correlation is negative, this whole last term turns negative, and so we come to the result that the lower the correlation between these two stocks, or securities returns, the lower the correlation, the less variance, the less uncertainty about the return on the portfolio. And we'll refer to that later when we talk about portfolio theory, and you'll see this formula, and we'll talk about the variance of portfolio returns again. And at that point, we'll be talking about diversification and saying, well, if you've got a diversified portfolio, the correlation is lower, then we get some benefits from that. Because if one's up when the other's down, that's okay. That smooths out the whole ride. It lowers the variance or standard deviation of the returns on the portfolio of the two assets combined. So let's take a look at the calculation here. We've got a portfolio that's 30% invested in stocks. That's WS, I guess, or WA. And standard deviation, 20%. And the remainder is in bonds, so that's 70% in bonds. And our standard deviation there is 12%. We're given the correlation of returns for stocks and bonds as 0.6. So a positive, medium, I guess, correlation. What's the standard deviation of portfolio returns? Well, we just have to use the formula. And so we've got the weight in stocks squared. We've got the weight in bonds squared. We had to square our standard deviations, 0.2 and 0.12. And then we've got 2 times weight in A, right? That was weight in stocks here, weight in A in our formula. Then we've got the weight in B. Then we've got the correlation and sigma A, sigma B. And because that's the formula for the variance of portfolio returns, we need to take the square root of that in order to get the standard deviation of portfolio returns. And so that's pretty low. I mean, when you look, we've got 30% in the stock with 20% standard deviation, 70% in bonds with a 12% standard deviation. If we just took the weighted average of that, right, 30% of 20% is 6, and 70% of 12% is 8.4. So that would get us like 14.4. Okay. But because they're not perfectly positively correlated, because this correlation is less than 1, there are some diversification benefits there. And so that's why we were able to come out with just 12.9 rather than just simply a weighted average of the standard deviations on our 2 stocks. Well, now we've got a joint probability function. We're going to calculate covariance from a joint probability function. Now, this is really nothing we haven't seen before, because we've got 3 possible outcomes, and now we have a paired outcome. So what this table is telling us, there's a 15% probability that the returns on A will be 20%, and the return on B will be 40%. So that's really the joint probability. So that's why we call it a joint probability function. There is a 15% probability of 20 and 40. There is a 60% probability of 15 and 20, and a 25% probability of returns of 4 on A and 0 on B. So we just do our same old covariance calculation. First, we need the expected value, right, to take the deviations from the expected value. So we take those probabilities and multiply them. Those are our weights for the outcomes. So 15% times 40%, and 60 times 20, and 25% times 0. That gives us an expected return of 18%. And same over here, 15% times 20 plus 60% times 15 plus 25% times 4. Add them all up, and we get 13%. So we've got our expected return on A and our expected return on B based on those probabilities in the table. So now that we have those, we got to do our deviations. So again, here's our expected return on A, here's our expected return on B. Okay? So we've taken for this first outcome, 20 and 40, 20 minus 13, 40 minus 18, multiply them together and multiply them times that 15% probability. And we do that for the other pairs. So we do that for a pair of 15% and 20% right here and here, and our weight there is 60% right there. And we do that for this last outcome of 0 and 4% as well. Add them all up, and we get a covariance of 0.0066. So that's covariance from a probability function, but very similar to what we looked at with a probability model, where we had a boom, we had a normal economy, and we had a slow economy. And Bayes' formula, everybody's favorite. What's the idea of Bayes? Well, the idea of Bayes' formula is that if we had some more information, we could update our expectation of probabilities. So we've drawn a tree here. We've got probability of the economy outperforming, probability of O, and we've got the probability of underperforming. So the probability of outperformance is 60. The probability of underperformance is 40. And then we've got our conditionals. The probability that shares will gain is 70% if the overall economy is outperforming, and probability of shares losing, of course, is 1 minus that, 30%. Now, if the economy underperforms, there's only a 20% chance. So the probability of share gains given the economy underperforms is only 20%. And the probability that shares will lose value, given that the economy underperforms, is 80%. So if we look at these joint probabilities, okay, so this is the probability of outperformance and share gains. This is the probability of underperformance and share gains. So we want the probability of outperformance given that there are share gains. So this is really working backwards. So what we're saying is, well, what if you knew that the shares gained? What would that tell you about these probabilities? And sometimes we call this the updated probability, given the information that shares have gained. So we're looking for the probability of outperformance given that we've had gains. Well, there's a formula you can memorize, and I find it hard to remember, but it's real straightforward to do this calculation on the tree here. Because first I'm going to look at the total probability, 42 and 8. So that's our unconditional probability that shares will gain. We don't know anything about the economy. There's a 50% chance that shares will gain. Well, if shares do gain, what percentage of the time is it associated with outperformance? Well, 42% of the time. So 42% of 50% of the time, when shares gain, we had an outperforming economy. Here, I've got some more formal red marks for you instead of my own here. So we're going to take that, the total probability of gains, 50%. Okay, what percent of the time do we have share gains without performance? And that's how we end up with 42% over 50%, so 84%. So we're going to update this probability right here, probability of outperformance, and say, well, if we had that information that shares had gained, then we can revise that estimate of outperformance and say, well, our new estimate based on that information is 84%. Now, that said, I know we don't use Bayes' formula anywhere else in the level 1 curriculum, and I also believe that I don't think it comes up at level 2 or level 3, and if it comes up at level 3 a few years from now, a couple years from now, you probably have to review it anyway. So see if you can get used to this tree, laying it out like that. So if you do get a question on Bayes' formula for a calculation, you'll be able to get it right. Okay, factorials for labeling. Now, a factorial, when we have 4 factorial, just as a refresher, that is 4 times 3 times 2 times 1. And there's a factorial key on your Texas Instruments calculator. So we've got 8 stocks, and we're going to rate 4 of them long-term hold. 3 will be rated short-term hold, and 1 will be rated sell. And we want to know how many different ways are there to do this. So the 4 that are rated long-term hold, it doesn't matter what order they're in. That's just one group. We've got to put these 8 stocks into one group of 4, one group of 3, and one group of 1. That's what we're up to here. And here's the formula for it. It is 8 factorial divided by 4 factorial times 3 factorial times 1 factorial. That is the number in each of our 3 groups. And that comes out to 280. So that's how many different ways we can put these stocks in this group of 4, group of 3, and group of 1. Now, choosing R objects from N objects. So again here, order doesn't matter. And if there's just 2 possible labels, we can use the combination formula or binomial formula. So let's look at an example. We have 8 stocks and we want to place orders to sell 3 of them. How many different combinations of 3 stocks are there? Now we're not talking about order, because we're not talking about 3 stocks, sell them in order. We're just talking about which 3 of 8 we're going to sell. Now, here's the formula for it right here, and here's an application of it with 8 and 3. We're really answering the questions. How many different groups of 3 can we pull from 8? Now, if you're using the Texas Instruments, the BA2 Plus calculator, there's actually, this is a function on there. And there's also one in PR for permutations. So C for combinations and P for permutations. We're going to use that when the order matters. So here we've just figured out that from 8, there's 56 different groups of 3 that we could choose. Now, when order does matter, and look at the wording here, you have 8 stocks, you want to sell 3 one at a time in a given order. How many ways are there to choose the 3 stocks to sell in order? So this is going to be more than the number of groups of 3, because now each group of 3 can be ordered in different ways. And how many ways can they be ordered? Well, go back here. See this term right here, R factorial? That's the one that goes away in the permutations formula. So that's our 3. So the term that's missing is 3 factorial. That's how many ways there are to order 3 stocks. So given a group of 3, we can put them in 3 different orders. 6 different orders. 3 factorial, 3 times 2. And so now we get a bigger number instead of what we had 56 before, I think. Now, given order is important, we've got 336 different ways to do it. And here's the calculator buttons for those solutions on the TI calculator. How many ways to choose 3 from 8? Okay. N is 8. We use the second function, the NCR key, and 3 is our R, and then equals, we get 56. If we do NPR in that same sequence, permutations, we get 336.